I met Sydney first in 1963 in Istanbul, where he and Shelley Glashow verified me the first time. And ever since, I've been an informal student of Sydney. I'm very grateful to Sydney for many things, and wanted to make sure this meeting happened. I've seen Sydney quite a lot over the last couple of months when we've talked about things. And I really want to assure you that although Sydney's not here in person, he's here in spirit. Sydney is still with us. He likes to see his friends. Because of his Parkinson's, he can't get around as well as he used to. But he's a little slower than he used to be. But he likes to see people who come over and visit in ones or twos and have delightful conversations. And he's still terrifying. Every time I've talked with him in the last couple of months, he's come up with Sydney that's extremely clever and to the point. And he will get the taste, and so he'll have the chance to enjoy all of the talks that we've had for the past 2 days. Ed Witten really needs no introduction. He came to the department first in 1977 as a postdoc and a junior fellow. He's worked in so many fields of theoretical physics: gauge theories, instant times, large expansion, supersymmetry, strings. His interpretation of the Jones polynomial, his legend, M theory, and as many times we're very interested to interpret what is the title of today's talk.
I'm slightly worried that I might have given a title that will be more interesting than the talk, but we'll try to avoid that as much as possible. So there's a very close analogy, which many of you will know, in many cases better than I do, while to others it might be new, between condensed matter physics and relativistic quantum field theory, as a result of which particle physics and condensed matter have many phenomena in common. So among them are the renormalization group, which was one of the actors, although slightly behind the scenes in the last lecture by 't Hooft, as well as a prominent character in some of yesterday's talks. Spontaneous symmetry breaking, both the chiral symmetry breaking that occurs in the strong interactions compared to many phenomena of symmetry breaking in solids, and finally dimensional transmutation, where a mass scale seemingly appears out of nowhere, as in the Kondo effect or the theory of strong interactions. Now, this analogy has a very natural explanation. You imagine a little box in space, here it is, and there's something inside the box. Inside the box, there's some kind of local quantum mechanical degrees of freedom, and what we're interested in doing is studying the large-scale behavior that is manifested at distances much bigger than the size of the box as a result of microscopic local degrees of freedom inside the box. Local means that they live inside the box, and you can write the Hamiltonian for degrees of freedom inside the box just in terms of their own fields and their immediate neighbors, without specifying what happens elsewhere. What happens elsewhere comes in when you solve the equations to try to determine the large-scale behavior. So this basic problem of having something at short distances and wanting to know what it does macroscopically where you make your observations is common to particle physics and condensed matter, and is the reason for the analogy. Inside the box are some local degrees of freedom. Their precise nature may not be important when we make observations at longer distances. They might be spins, electrons, relativistic fields, or whatever. And it's because of the common problem of finding what happens at big distances from local degrees of freedom at short distances, whose precise nature may not be so important, that leads to this analogy. Now, condensed matter and particle physics also have obvious differences. Largely, most obviously, in that in condensed matter, one feels for the most part that one knows a sufficient system of equations, the many-body Schrödinger equation. And one is always working forward from there, while in particle physics, part of the problem is to determine what's a sufficient set of equations. On the other hand, while the differences are obvious, the analogy between them is quite deep. Yet it may have a key limitation, which we'll come back to at the end, and in a way explaining this limitation is the reason for giving the talk. Now, in the early days of the modern theory of solids, which of course means the theory of solids based on quantum mechanics, the focus was on quantitative calculations starting from the many-body Schrödinger equation. One had the Schrödinger equation, so one wanted to solve it as much as possible to determine energy levels and band structure and so on in solids. But the modern focus is a little bit different. The focus nowadays is less on quantitative solution of the Schrödinger equation and more on qualitative phenomena that emerge macroscopically through the magic of the renormalization group and the cooperative behavior of many degrees of freedom. And it's there that the microscopic details don't matter so much. They could be electrons and nuclei obeying the Schrödinger equation, or they could be something a little bit simpler. At any rate, there are local degrees of freedom that lead to surprising cooperative effects at long distance, and much of the focus is on elucidating those macroscopic effects. These are the emergent phenomena, to use a phrase often given in the condensed matter world, that are responsible for much of the richness of condensed matter physics. Many long predate the modern era. For example, hydrodynamics long predates the understanding of it in terms of atoms and ultimately electrons and nuclei. So there the emergent phenomena was studied long before there was much understanding of what it emerged from, while numerous other emergent phenomena, like the many forms of the quantum Hall effect, are modern discoveries. What about particle physics? Well, relativistic quantum field theory began by literally quantizing what we see. The electromagnetic field, the basis for the light waves that we see, as understood by Maxwell's equations in the 19th century, was put through the mill of quantization, saying that the position and momentum don't commute, but there's a minus IH bar in the commutator. And that was the beginning in the 20s of relativistic quantum field theory. It was a little harder to include electrons. That took a lot of formal discoveries. The Dirac equation for an anti-commuting electron field of spin half, filling the Dirac sea, and interpreting the holes in the Dirac sea in terms of antiparticles that were then observed in cosmic rays, and so on. It was difficult to develop perturbation theory. One had to understand renormalization, which in fact wasn't accomplished for a quarter century until after the basic equations had been first written down. But once perturbation theory was understood, it was entirely adequate for understanding quantum electrodynamics because the fine structure constant, E squared over h bar c, is so small. And as a result, physical observables could be computed with astonishing accuracy. Now, one could make an analogy between QED and condensed matter for the basic reason I said, that you start with local phenomena whose precise details don't matter, and then you determine the consequences at long distances. And in fact, some people did make this analogy, but the analogy did not seem to go far, at least to most physicists, because the problems arising in the two fields were so different. The problems in QED were a little bit more like algebra, formal constructions, finding the right rules, after which you could systematically calculate in perturbation theory, whereas the nature of what one has to do in condensed matter is quite different. As I just said, in QED, even when one was making, as Dirac did, a dramatic and completely new prediction of antimatter, the reasoning was based on understanding how to interpret the equations, rather than on finding some dynamical approximation or deducing some emergent phenomenon in a magic transformation from short distances to long distances. So this was in sharp contrast to what goes on in much of the most interesting condensed matter physics. Well, so much for QED. What about the electroweak theory? And here, the model could not be constructed by literally taking what we see at the classical level and then quantizing it, because, among other things, the W and Z bosons hadn't been discovered, and secondly, because of their huge masses. One can't really study them as semi-classical fields like the electromagnetic field. So one wouldn't have had a a classical limit to quantize. So the reasoning that led to the SU2 times U1 model was really quite different than what led to QED, and I don't have time to review it now. But we might ask, for the present lecture, the following question. Once the electroweak model was constructed, does it exhibit emergent phenomena in the sense of condensed matter physics? Does it rely on phenomena that can't be understood directly from the underlying degrees of freedom and developing the proper rules for quantization and perturbation theory? This question really is one of the big unknowns that hopefully will be cleared up at Fermilab or the LHC in the next few years. But in the original and still standard form of the model, the answer is taken to be no. All fields are weakly coupled, and the observed phenomena in the original form of the SU2 times U1 model are direct reflections of the underlying fields. There are all those tricks in learning how to quantize the underlying fields because of their Yang-Mills non-abelian nature. Gerard reviewed that period at the beginning of his talk in the last hour. But once the rules of quantization and perturbation theory are understood, in the original form of the electroweak model and still the standard form, the phenomena are taken as fairly direct reflections of the underlying fields. Moreover, this seems to be in good accord with the experimental evidence so far, which appear to favor a light and elementary Higgs boson, and to agree with that interpretation more straightforwardly than with the competing theories. However, the central phenomenon of the model is gauge symmetry breaking, somewhat analogous to the symmetry breaking that occurs in a superconductor, where the mechanism is interpreted as a dynamical emergent phenomenon. And the analogy is so striking, well, both because that analogy is so striking and because experiments are not yet truly decisive, the question remains open, even though the original form of the model is held up so beautifully. Well, what about these strong interactions? The strong interactions are where physicists really learned about strong coupling and emergent phenomena. So there were a few papers before QCD emerged as the theory of strong interactions on strongly coupled behavior in relativistic field theory. A famous example being Schwinger's solution of the Schwinger model, quantum electrodynamics in 2 dimensions with zero bare mass for the electrons. So such results existed, but they were isolated results and not part of an intensively studied story until quantum chromodynamics emerged and made the central role of such questions clear. Quantum chromodynamics is the theory of strong interactions, and this is all about emergent phenomena. At short distances, there's a microscopic description by quarks and gluons, none of which we see in a simple fashion in experiment. At long distances, there's a completely different cast of characters. There are the pions, the protons and neutrons, and rho mesons, and so on, which we believe are connected to the quarks and gluons in ways that even today we don't understand as well as we would like to. We can see the quarks and gluons manifested in experiments when we find experiments such as Bjorkane scaling or jets in E plus E minus annihilation that probe the microscopic properties. So carefully selected special experiments probe the existence of a description of the theory by quarks and gluons. And that's the larger part of why one has confidence that quantum chromodynamics is correct. But at large distances, what we see is a completely different cast of characters. And as Gerard well explained in the last lecture, this disconnect between the what we actually see and what one had to assume in a Yang-Mills theory made it hard for a long time to believe that the strong interactions were described by Yang-Mills theory until asymptotic freedom gave a rationale, not really a computation, but a rationale for why the coupling would become strong in the infrared, and there might be a totally different set of phenomena and characters in the infrared from what one had in the ultraviolet. So for decades before asymptotic freedom and QCD emerged, quantum field theory had been understood mainly as a formal machinery for generating perturbative Feynman amplitudes. And quantum chromodynamics changed it because there were these strong coupling phenomena. First of all, perturbation theory wasn't adequate to understand them. It wasn't a good approximation quantitatively, but it didn't even give the right picture qualitatively. The right picture qualitatively was in terms of a completely different cast of characters. So QCD led to a new phase where relativistic particle physicists became intensely interested in strong coupling problems. The goal was to understand what really are the crucial mysteries of the strong interactions. Quark confinement, the generation of mass out of seemingly nothing, starting with the massless particles of Yang-Mills theory, chiral symmetry breaking, the emergence of the pions with their special properties at low energies, and all that. And these are questions that even today we don't understand as well as we would like to. We have the computer simulations, which give our strongest evidence that it works. We've got a lot of pencil and paper calculations that shed some light on different aspects. But we'd really like to have a more powerful pencil and paper understanding that would at least convincingly show that the right theory, not some simplified analog problem, led us to the right universality class, to use the jargon, at long distances. And we're still short of that. Many of us believe that the one over n expansion that was one of the heroes that got slightly short shrift, but still one of the heroes behind the scenes in Gerard's talk, might ultimately be the clue, but it hasn't been implemented fully. Sidney Coleman played a big role in all this period, helping us understand and digest the lessons of QCD. Gerard mentioned a few such episodes in his talk, and also initiating the study of analog problems in 2 dimensions. Well, broadening the study might have been a better word, because there were fragmentary results, such as Schwinger's paper that I already mentioned. But Sidney greatly enriched our understanding of what could be done with all this. And here are 2 of the papers he wrote in that period. One was already mentioned by another speaker on the Sine-Gordon-Turing equivalence. Another paper that had a lot of influence on me, I remember, was his paper on the massive Schwinger model, where he basically took Schwinger's solution of the massless Dirac equation, of quantum electrodynamics in 2 dimensions with massless electrons, considered the massive case, which he could not exactly solve, but about which he could say fascinating things. Now, in this new phase of strong coupling investigations in relativistic field theory, a prominent role was played by many techniques that were previously more familiar to condensed matter physicists, such as high-temperature expansions of lattice models and lattice simulations and other methods. And our understanding of the dictionary between condensed matter and relativistic field theory became much more perfect. One of the important chapters that I haven't had time to mention is the analogy that was largely introduced by Ken Wilson, among others, that the ability to renormalize a relativistic field theory and to take the continuum limit, to remove the regulator, and to define an exact theory, not just a perturbative approximation, is a phenomenon very similar to something that's seen in the lab. The occurrence of critical points, for example, in a fluid, in water at a special temperature and pressure, where one observes a critical point, and according to Wilson, the fluctuations that one sees at this critical point, which are dubbed critical opalescence, where the water literally becomes milky as you approach the critical point, those fluctuations are actually described by relativistic field theory. So that statement, in a way, is the purest form of the analogy between condensed matter and particle physics. Now, I've tried to say a little bit about what emergent phenomena mean or don't mean for the usual particle forces. I've explained that this notion has to do with the way of thinking that one doesn't need for quantum electrodynamics. One does need for the strong interactions. And we don't yet really know whether we need it to understand the weak interactions. But we hope to settle that question in the next few years, since experiment is reaching the energy scale where the Higgs boson, or whatever does that job, must lie. But of course, I've left out one of the known forces of nature, and that's gravity. What might emergent phenomena mean for gravity? And it's here that we're going to run into a limitation of the usual analogy between condensed matter and relativistic particle physics. And I'll also tell you a little bit at the end of an alternative analogy, which at least in some situations does hold up in the presence of gravity. Now, gravity is different from the other particle forces for a large number of reasons, but for us the basic difference is that gravity spoils the usual paradigm that leads to the analogy between condensed matter and particle physics. The usual paradigm, as I told you before in words, but now I'll at least come a little bit closer to writing a formula. At least I wrote down 5x, the name of the field. The usual paradigm is that you start with local degrees of freedom, 5x, at short distances, and out somehow come then phenomena at long distances which you wish to observe. This is what we're doing in particle physics, because in particle physics we always feel that whatever we're measuring is a long-distance approximation to something even better that happened, or some better understanding that existed at shorter distances. And it's what one does in condensed matter, because you can have a lot of fun with band structure, but in the long run, the greatest richness comes from the fact that such surprising phenomena happen at long distances that are so unobvious in terms of the microscopic laws. So this is the basic paradigm in much of condensed matter physics, and also in particle physics without gravity. But there's a problem with this paradigm if we incorporate gravity, and that has to do with the fact that general relativity is based on general covariance, covariance under arbitrary coordinate transformations of space and time. And x, which labels a space-time point, isn't a gauge-invariant notion. So we cannot expect in a theory of gravity to have a gauge-invariant local observable 5x. 5x might be Yang-Mills invariant, but it's not going to be Einstein invariant. It won't be invariant under Einstein's general coordinate transformations, because x isn't invariant. So we're not going to have local observables of the usual kinds, and we can't specify local degrees of freedom in the usual way in a theory with gravity. As far as the first paper I know of that articulated this point in some detail was by Bryce DeWitt in about 1966, where he was able to discuss a perturbative S matrix for a gravitational, for Einstein's theory in an asymptotically Minkowskian world, but he observed that he would not similarly be able to define matrix elements of gauge-invariant local operators. So not having 5x as a gauge-invariant entity is one way of saying it. Another way of saying it is to draw the picture that we used before. The usual picture for the usual analogy between condensed matter and particle physics, you imagine a little box that's very small compared to the scale of your experiments. And something is specified inside the box, and you want to know what happens way, way outside the box on larger distances where fields or degrees of freedom within many neighboring boxes are contributing collectively. This framework is lost when we include gravity, because gravity makes the box fluctuate. It doesn't make sense in general relativity to say here's a box with some degrees of freedom inside it, because the box itself is fluctuating with fluctuations in space-time. So we can't make an asymptotically Lorentzian world out of a lot of little regions, each of which has its own degrees of freedom that are then coupled together in a local fashion. The basic framework is wrong. This is, in pictures, a version of what I said in formulas by saying that there was no local field 5x. So there's no local field 5x because x isn't invariant. What x would have been was a point inside the box, but the box is fluctuating. You don't know where it is. It might have collapsed into a black hole that then reemerged from Hawking radiation. So the usual analogy between condensed matter and particle physics doesn't work in the presence of gravity, But it seems that there may be a new analogy, as I'll indicate at the end. Whatever we do in understanding gravity, we're not going to start with a conventional theory of non-gravitational fields in Minkowski spacetime and generate Einstein gravity as an emergent phenomenon. So, what are the crucial words here? So, conventional theory, that's a theory without gravity, a theory of non-gravitational fields that starts its life in a flat spacetime. We're not then going to generate gravity as an emergent phenomenon. We're not going to, because the conventional theory had gauge-invariant local fields, phi of x, or trace e squared of x, or something. The conventional theory had some kind of local observables. That's what conventional theories are. They're theories of relativistic local fields, and if there are gauge symmetries, you put them together in gauge-invariant combinations, and you get gauge-invariant local fields that obey axioms that you can read about in textbooks. That's what won't exist in a theory with gravity. So, if that structure does exist, then you can't generate Einstein gravity at long distances because Einstein gravity would prevent that structure from existing. There's even a theorem that says this. I'll get to it in a second, but this last sentence is what I just told you. The conventional theory would have local operators phi of x, and the existence of local operators phi of x makes gravity impossible. There's even a theorem about this, sometimes called by kind people the Weinberg-Witten theorem, which was proved with some strong cues from Sidney Coleman in 1980. And what the theorem says is that a massless spin 2 particle cannot be generated as a bound state if you start with a conventional theory. A conventional theory has a local stress energy tensor. So phi 4 theory, Yukawa theory, Yang-Mills theory, they all have local stress energy tensors. That was assumed by Einstein in describing general relativity. The left-hand side of his equation was the Einstein tensor, and the right-hand side was the stress energy tensor. So any theory that can be coupled to gravity has a T mu nu, otherwise it can't be coupled to gravity. Einstein assumed there was a T mu nu. If you start with a T mu nu, then Weinberg and I showed, with a little help from Coleman, that you can't then have a massless spin 2 particle in the infrared. It has nothing to do with any further microscopic assumptions. You simply consider the matrix element of the stress tensor, T mu nu, between initial and final states of the massless spin 2 particle, and you reach a contradiction after a little while. Now, this theorem reflects the fact that you can't get gravity as an emergent phenomenon starting with a conventional theory in flat space. But this theorem is really a mathematical explanation of a fact that we should first understand intuitively. And it really starts here. The whole idea of the relation between short distances and long distances and getting emergent phenomena starts from this picture with the little box that has something inside it. That picture doesn't make sense with gravity. And then a little bit later on, the theory without gravity had local operators phi of x, and the theory with gravity doesn't. So for a variety of qualitative arguments along those lines, you can't, whatever else you're going to do, you can't start with a conventional theory and generate gravity spontaneously. And then there is this theorem. And so if you think what I'm telling you is wrong, you can look for a loophole in the theorem, and I'm often contacted by people who are doing so. And I always tell them that that's good, but they should also go 1 or 2 steps farther back and try to find loopholes in those other arguments. If we want to generate gravity as an emergent phenomenon, we must go farther and generate space-time itself as an emergent phenomenon. If we started without space-time, we wouldn't have had x, so we wouldn't have had phi of x. And therefore, we wouldn't have had any abstract reason that gravity couldn't emerge. We wouldn't have had x at short distances because we assume space-time isn't fundamental, and we wouldn't have x at big distances because we would have gravity. So a consistent point of view, a possible point of view, is that at short distance, well, at a more fundamental level of understanding of nature, short distances is here an inadequate turn of phrase, but at a loftier, more refined plane, there might be no space-time, and then macroscopically, space-time with gravity might emerge. This is conceivable in the sense that no general argument excludes it. It might be wrong, like any other suggestion, but there's no general argument against it. And there even are examples in its favor, as we'll discuss shortly. So in fact, it's generally believed by string theorists, although certainly not understood in any detail, that what I've just said is exactly what happens in string theory. That string theory, as we compute it in perturbation theory, is some kind of manifestation of something more primordial that we don't understand well, but which does not have space-time built in. And that space-time and gravity and all the stuff that come out are some kind of manifestations that occur if you make suitable assumptions about what solution you're looking at or what quantum state or whatever the right language is. But anyway, the general thought of string theorists is that all the usual stuff is some kind of manifestation of something more primordial that we don't know about. So the view is that space-time and the fields and particles in it are a kind of large-scale approximation that's generated from more primitive variables of which we have hints, but certainly no general understanding. The reason we believe this is that since early days of studying string theory, we've been constantly finding phenomena that seem incompatible with the idea that space-time were truly fundamental. I could do a better job if I was given to talk just about this, expanding this one sentence. And then I would start with very early examples, probably involving the Veneziano amplitude and some of its properties, which gave to the birth of string theory, and then many things that were discovered after that. And then eventually I would have gotten to the more recent examples that I wrote here. Mirror symmetry, which is a non-classical transformation between different space-times, and then more general topology changes, and all kinds of non-perturbative symmetries and dualities that are seemingly incompatible with the idea that space-time is a really fundamental notion in a basic description of the theory. This doesn't come with any money-back guarantee, certainly, but the study of all these things has convinced at least the great majority of string theorists that we're looking for a better understanding at a level that would start with something more fundamental and then ultimately give rise to space-time, particles, fields, gravity, and all that as a long-distance approximation. Now, we don't have any good general point of view about this, but there actually is a situation, well, there are a few situations in which we have some idea of how this works, but to keep this simple, I was only going to mention what's perhaps the prettiest, and that comes from Moldesena's gauge-gravity duality, which gives us a picture of space-time as an emergent phenomenon. And this picture works as follows. So there is a relation between an ordinary theory and gravity. You can start with an ordinary theory and generate gravity. What I told you was that you can't start with an ordinary theory in Minkowski space and generate gravity. I didn't say that you couldn't start with an ordinary theory somewhere and generate gravity, as long as you generated space-time, the space-time in which you observe gravity, along with the gravitational field that you observe. In this picture, there's gravity somewhere, but there's a gauge theory, a conventional theory without gravity somewhere, but it's on the boundary. I've drawn the boundary as a circle. I drew it at finite distances just so I could draw it. But in a better picture, that would be a virtual boundary at infinity, and also we should be in a larger number of dimensions. But on the boundary, we do have a conventional theory. And in Moldesena's example, or at least his simplest example, that conventional theory is a gauge theory. But in more elaborate examples, that boundary theory is a conventional theory of a more general kind. All I mean by conventional theory is a theory without gravity. A theory of local degrees of freedom without gravity. At the very vague level at which I've described both particle physics and condensed matter physics today, the boundary theory lives in that world. It's a normal theory with local degrees of freedom and without gravity. Now, this normal theory, however, is strongly coupled. So since it's strongly coupled, you can learn in the textbooks how to do perturbation theory, but that doesn't tell you what the behavior is. To find out the behavior, you need to learn to deal with the strong coupling problem, and non-perturbative phenomena might emerge in the infrared. For example, in the case of QCD, the phenomena that emerge are pions, protons, quark confinement, and all that stuff. And here, the phenomenon that emerges is a new description in a different world with one more dimension, d plus 1 instead of d, and with gravity. So you start with a conventional but strongly coupled theory, and when you learn how it behaves in the strongly coupled regime, the answer is that it generates space-time and the gravitational field together. So the space in which you observe gravity is this d plus 1 dimensional world, which wasn't part of the elementary description. The elementary description in terms of a conventional theory was a gauge theory on the boundary with local degrees of freedom but no gravity. You solve it, you find an alternative description with one dimension more and with gravitational fields propagating in the bulk. So this is an example where one started with something else that wasn't four-dimensional space-time and didn't have gravity, and you generated space-time together with gravity together. So there is an analog condensed matter system, but it lives on the boundary of the universe. So there are a few other examples, but this is the prettiest setup in which we understand concretely how to generate space-time and gravity together, starting with something else that had neither. And we don't understand it well. It's presumably only a special case of a more general story that we don't know. But although we don't understand it well, it's given lots of nice calculations, some of which elucidate gravity and some of which elucidate gauge theory. The reason that can happen is simply that if I tell you that a world on the boundary without gravity, but with gauge theory, is equivalent to a world in the interior with gravity, you have a dictionary that you can read in one of two ways. If there's a question you don't understand in terms of gravity, you can interpret it as a question in gauge theory that perhaps you can answer. And conversely, if there's a question in gauge theory that you don't understand, you can interpret it in a question in gravity that you can perhaps answer. So you have four types of questions. Those that you can answer either way, and then they work out, and that's what convinces you that Maldasena's duality is correct. Those that you can answer one way and not the other, and then you learn something. And those that you can't answer either way, and then you have to wait for somebody else to come up with a clever idea. So in the process, even though you don't understand the general story of which this is a special case, you can get lots of novel understanding of quark confinement, black hole entropy, Reggie behavior of gauge theories, and all kinds of other fun things. So at least you can have fun while waiting for Fermilab or the LHC to tell us about the weak interactions, and while waiting for somebody to come along and tell us what the general story is. Thank you.
Are there questions? Yes. Sure.
In the ADS-CFT examples you described, would you agree that while space has often emerged as emergent, time has been less emergent?
From some point of view, one would describe it just the way you did. But from another point of view, the way I set up my talk, what can't happen is to start with these space-time that you're planning to observe gravity, and then generate gravity in that space-time. So this setup, you can say a lot of interesting things about it. But one interesting thing, the only point I really tried to make in my talk, is that that gravity is generated out of loosely speaking nothing, but it's generated together with the space-time. I feel that perhaps most of the answer might be too technical.
John.
Although I'm not actually sure I understand what you meant by emergent phenomena. If I understand correctly, then I agree with your statement about QED, or you call it in the sense that due to the renormalization process, we know that we are not sure about what are the problems.
QED might, as a whole, be an emergent phenomenon from something else. That's really what you're saying. But if you simply take QED...
No, I say that.
But it might be. But if you take... My point was more narrow. If you take QED as it is in the textbooks, and as it's defined by practitioners who calculate minus 2. I think I gave a reasonable account. I don't disagree with you. Of course, there could be an unknown chapter.
Yeah.
That could be so even if QED were normalized for short distances. It might make sense mathematically short distances, and that mathematically correct theory might in fact be wrong. So I agree with what you said, but what does that have to do with me? It's more, I would have said that anything that we understand at any level might be only an approximation to the truth.
But I'm saying that renormalization also strips the condition.
You know, I had a problem, which is I read too fast. But I planned the talk right out of time before I had to about it. I can draw the picture again, but we wouldn't be, to properly explain the picture, maybe the end of the course, which is a 2-year course, and to eventually explain how one becomes convinced about this matter. Condensed matter is just a conventional thing with local distribution. What I'm saying here is that one has in this situation a convincing picture where there is a description by conventional theory with local degrees of freedom. It doesn't live in the space-time where gravity is observed. Yet there is also a description in terms of the space-time in which gravity is observed. The space-time and the gravitational field are both emergent phenomena from the point of view of the conventional description of the matter.
I was confused with the term boundary. So by boundary only you mean one dimension less than what's
Yeah.
Bernie?
Is there any way supersymmetry to be emergent or supersymmetry?
Well, I better say no because, I better not say no because presumably before we get to supersymmetry, let's take point trace symmetry. So it's a property of, space-time. Paul's theory is a reflection somehow of something primordial in the context of string. The string theory is a right. One would expect that would be the intentional conclusion.
Maybe it's possible to destroy particles as used in defects in some sort of space-time sequence.
The second half of your sentence, you asked about defects and crystals, is a little bit too narrow. But more broadly, the proton, QCD is an example. So the microscopic description is by quarks and gluons. The macroscopic description is by pions, protons, neutrons, and so on. So the iron particles are not simple manifestation of the underlying forces. And many of us, going back to Hooke, who mentioned this very briefly, suspect that there's a third description of the same theory by a string theory with 1/n as the string coupling constant. So if we have that at our disposal, we have a richer three-corner picture where the phrase emergent phenomena wouldn't do full justice to it.
Isn't the pion a better example than the nucleon? Because the nucleon can be thought of as, in some sense, a bound state of three quarks, which the pion is very badly described as a bound state of quark. But also, in answering the question about supersymmetry, do you really mean gravity or do you mean supergravity?
Well, it would be nice to hope that we'll see what we're really carrying on and teach us that supergravity is running relatively accessible distances. So then we might rephrase this question in terms of supergravity. But
Can you really find a theory in which you get gravity rather than supergravity?
Oh, I see. I think the answer is yes. In other words, I think if I had time to play that, I remember that. I think that the examples are all reduced, knowing about supersymmetry examples, and then considering the normalization details of like supersymmetry. I'm almost sure if I will have a convincing example.
Orbital. You got orbital.
Well, I wasn't sure whether Steve was asking me about unbroken or fancy focus. It might be that all these string theories have, if they don't have supersymmetry of relations, have supersymmetry of some energy. Okay. What I might manage to give is polish up with before coming. Is an example of spontaneously broken supersymmetry.
Yeah.
So one example might have been, one continuation of previous one. One example might be the orbitals of supersymmetric one which breaks supersymmetry. So that's
there's potentially an example, but we need to check that they're stable. So some of them are potentially destabilized by one of their infections. So what I would have done, if I anticipated this question, is to bone up the home and remember some non-supersymmetric models with no massless modes that could lead to instability. And then I would have had a better answer. See, there are certain numbers like that.
It seems to me that the gravitational problem story is a little bit more nuanced than that, because at the classical level, I can do dynamics, what I see. That is to say, I can derive classical which at the end of the day solves Minkowski and turns out to be Einstein as a classical. The problem occurs when I context each case of QEDS or each bible.
Well, I said something very precise about the difference between QED and gravity. QED has gauge and direct local operators, like psi bar psi or FD. Any theory of gravity does not. Let's call them theories of type A and type B. They do or don't have local operators. So, if you have local operators, that's money in the bank. Whatever's going to happen at long distances can somehow be interpreted in terms of those local operators. So, a theory with gravity doesn't have them. So, you might, conversely, if you think you have local operators, you might be wrong. In a sense, that's the situation many technical theories in general. Because general optimistic effects are so weak. But one doesn't always emphasize the difference I emphasize between theories with and without gravity.
Bob?
Another particularly amusing emergent phenomenon that didn't mention is that vector dominance is equivalent to the emergence of a spontaneously broken flavor gauge center. Fundamental color gauge center.
You might know that there are some attempts at phenomenological explanation of this in these elaborations of the Montana type model, where one makes models. First of all, one makes models where one actually can capture chiral symmetry. There's one by two Japanese authors, I can't remember the names. They had a nice model where they could demonstrate chiral symmetry breaking from an elegant geometrical construction. And then they investigated what you just asked about, and it worked perfectly. The reason it can't work exactly, and it's hard to see it working exactly, is that the n-exact formula would be a sum over all spin modes. And it's unclear why it's a good approximation of saturated as well. There's a lot of paper that's worth it.
Well, this discussion could go on for a long time, and I think this is a very fitting talk for the last talk of the conference. And before thanking Ed again, I would first like to thank all the speakers who've come here. You've done a wonderful job, and thank you for not having to be convinced to come. Everybody wanted to come. Thank the audience for spending your Saturday and weekend here. And especially thank the staff of the Harvard Physics Department who worked so hard to make this event run smoothly. Barbara Drauschka went crazy, and we can all thank her that this meeting went off without many hitches, not major ones that I've heard about. And now I think we should thank Edward Witten again for a wonderful, stimulating talk, which Sydney will really appreciate.